And you also.
Okay, I want to start notes for implicit differentiation. Quiz is still scheduled for tomorrow. As far as I know, tomorrow is going to be regular bell schedule. But if something changes in the afternoon, I'll let you guys know. Okay. I think yesterday and today were map testing, but I'm thinking that map testing will get pushed to a different day for math.
Oh.
But that's what I'm thinking. They haven't confirmed anything. So once I get confirmation, I'll let you guys know either way. But I'm thinking we're preparing for tomorrow being the quiz. Okay. But if something changes, I'll let you guys know. But either way, I will confirm through remind about the schedule for tomorrow. Okay. All right. So now implicit differentiation involves equations where your y variable is not defined by itself. So here is an example of an explicit equation, such as y is equal to x plus 16. This is explicit because we have the dependent variable by itself, and then we have our independent, our dependent variable by itself, and then our independent away from the dependent. So there's only one y variable, and that y is by itself. And typically with explicit equation, we're dealing with a nice function. Okay, so for any x value, we're only getting one y value. So we're on page 11 here. Okay. Now, implicit equation is where our y is not quite by itself. So typically, implicit equations are equations where typically potentially not a function. So many times implicit equations are not functions. So anything that is done to the y where y is not by itself, or it's being attached to something else, or there's multiple y's, we have something called an implicit equation. But we can still find a derivative for an implicit equation, even though it's not by itself, even though the derivative variable is not going to be by itself. Okay. So here is what happens when we find the derivative. Okay. So in terms of x, if I want to find the derivative of x, what's the derivative of x? It's just 1. Okay. Now, what's hiding is the fact that we're finding the derivative of x with respect to x. And so we never have to worry about that because that just goes away to 1. So it's just equal to 1. Right? Because we're finding the variable with respect to itself. Okay? Same thing here. If I want to find the derivative of x squared, it's simply 2x. But we never have to worry about the fact that dx over dx is part of that process because it just goes away. So we just always leave that alone. Same thing, e to the 5x becomes e to the 5x times 5. Technically, there's a hiding dx over dx, but we just wipe that out. But if I want to find the derivative of y, okay, the derivative of y is 1, but I'm finding the derivative of a dependent variable with respect to x, and so a dy dx is going to pop up. Same thing, right? If I ask you what the derivative of y is equal to x plus 16, you would say the x becomes 1, and then y just becomes dy dx. Now, the left side, we never thought of the left side as something that we're doing calculus. We just thought, oh, that's just notation, right? Y becomes y prime, or y becomes dy dx. But now we're going to have to deal with calculus involving the y because the y will no longer be by itself. It may not always be just from y to dy dx. Okay. So if I want to find the derivative of y squared, well, what's y squared's derivative just by itself? 2y, right? And we're going to attach dy dx. Okay, because we're asking for y's derivative with respect to x. Okay. Before, if we found the derivative of x with respect to x, it just cancels out. But the derivative of y with respect to x, these are two different variables. We have to keep track of that. That is a derivative variable here. Okay. Same thing here. E to the 5y becomes e to the 5y times 5. And if we ask for y's derivative, we're going to get dy dx. So anytime you're asking for y's derivative, and this is not by itself, you always have to find the derivative, whatever derivative rule that you need for that function or for that expression. But then you need to immediately keep track of your derivative variable here with the dy dx. All right, so implicit differentiation example. If I want to find the derivative equation for this equation, the derivative for this equation, I need to keep track of my y and keep track of the variable. Okay, so let me go through it step by step. So the first step is we take the derivative, right? So whatever derivative rule that we see, we're going to attach it. But then each time our derivative of y is involved, you're going to include a dy dx. You're going to multiply that term with a dy dx immediately after. Okay. So let's go ahead and find each of these derivatives. Everything can be done using power rule. So y squared becomes what? 2y. Now I'm asking for y's derivative, so I need to also include a what? dy dx. Yeah. So as soon as I find a y's derivative, I'm going to include a dy dx. Okay. Minus. Squared. Yeah, 15x squared. If I'm finding the derivative of something involving x, nothing special that needs to be done. It's just going to be how we normally do it. Technically, there's a dx, but we can just, that always wipes out, so we never have to worry about it. Okay, equals, what's 3y's derivative? Just 3, but then even though the y disappears, we are asking for y's derivative, so we still need to include a what? dy dx. Questions so far? So that ends the calculus portion. Now we're just trying to algebraically solve for dy dx. Before, we never had to solve for dy dx because the y was always by itself, and then y just becomes dy dx, and we are instantly able to get to the derivative equation without having to do a whole lot of rearranging. But here, now that your y variable is stuck inside the equation, we have to do some rearranging to get that dy dx by itself. So what we're going to do, step 2, we're going to gather all the terms with dy dx. Think of this as a separate variable here. We're going to gather all the terms with dy dx on the left side. It doesn't have to be the left side, but that's my preference. Everything on the left side, because I like to have that my derivative variable on the left side, and then everything else on the right side. So I see 2 terms with dy dx. So these 2 terms I'm going to try to group together or gather together on the left side. Any questions so far? Okay, so remember, our goal is to try to get dy dx by itself. So we're going to factor the dy dx. In this case, there may be other common factors, but we don't care about it. We just want to isolate dy dx, so we're just going to factor the dy dx out. And we're almost there. If I want to get dy dx, what's the last thing that I can do here to isolate that variable? Divide. Yeah. So my dy dx is equal to 15x squared over 2y minus 3. So this is my derivative formula, my slope formula for whatever this graph looks like. Now, what do you notice about this derivative formula that looks different than previous derivatives that we've worked in the past?
You have to plug both x in.
Yeah, so before with functions, the derivative only required the x value. But now the derivative requires the x and y value because our equation are no longer functions. Let me show you what that means. Normally, if I had a function, right, all I need would be the x value. The x value will tell me the location of that curve, and I can just find the slope using that slope formula. However, if your equation looks like this, right, let's say it's a hyperbola, and if you just give it the x value, the formula is not going to know, right? So, okay, if you give me the x value 3, are you talking about this point or are you talking about this point? It doesn't know. It needs more information. So you need to give it a full order pair. You need to give it a 3, 4 versus a 3, -4 so that it knows, okay, you're talking about this point. You want the slope of this point and not this point. So the reason why x and y shows up on the derivative is because you have some conflicting overlapping equations with overlapping y values, and the equation needs to know more detail if you want to find the derivative at a point. Okay, so that's why um, these equations require more than just the x and y value when it's asking for the slope. But once you give it the x and y value, it operates the same way as any other derivative. You give it a value, order pair, it'll give you a number, and that number corresponds to the slope or the steepness of that specific point on the curve. Okay, so we're just going to practice finding the derivative equation of these graphs. Okay, so let's look at number one. Number one is nice because these are only requiring power rule. And this is something that I want to point out here is if you're trying to decide, wait, did I get all the dy dx's that I need to? This is a quick way to check. You see how there are 2 instances of y's that show up in the original equation? That means that you're going to be expecting 2 instances of dy dx that show up in the derivative equation. Okay. I think the mistakes or the common things, some mistakes that I see in the past is I see some students, they feel like they're only going to include dy dx if there's a y showing up. But sometimes we also include dy dx if there's no y show up because the y disappears, right? 3y becomes 3. We're still asking for y's derivative, so we still need that dy dx. So we don't only include dy dx if there's a y left over. We include a dy dx if there's a y involved in the original equation process that requires that needs derivative. Okay, so maybe a better way to do it is count how many instances that you see of y's in the original equation, and that's how many dy dx's you expect to show up in your derivative step. Okay. All right, so let's try number one. I'll work through the first step and then you guys can finish it. Okay, so what's the derivative of 3 of y cubed?
Times 2.
Good, times dy dx, right? We need that dy dx. Minus equals plus 2 dy dx. Yeah. All right, so see if you can follow the rest of the steps. We're going to gather all the terms on the left side of the equation with dy dx, and then move everything else over to the right side. You're going to factor the dy dx out, and then you're going to isolate dy dx to get that derivative variable by itself. Okay, any questions with one? Okay, so I want to make sure that we can spot when implicit is needed. Basically, if you see anything done to the y's or y is not by itself, you know there's implicit, right? But if it's a nice function, if it's like y equals and everything else on the right side in terms of x, you know that it's just a nice function. You can just find the derivative, no implicit involved. But here we can obviously tell the need for implicit. There's two y's. There's y's with cubed on it, right? So anything that where something is strange about the y variable, that's when you know to do implicit. Okay. For number two, how can you tell that we need to involve implicit? Yeah, the y is inside the sine function, right? So that's something where that y is obviously not by itself. There's only one instance of y, but it's obviously stuck inside this trig function. So if I want to find the derivative, I gotta do it implicitly. Now, what's involved here, though, if I want to find the derivative? Can you chain rule and what? Product, good. So there's an outside portion here, which is that sine parentheses. And then there's the inside portion, which is that xy, but then that xy is going to require its own product rule. But chain is going to come first. We're going to take care of that outside inside, but once we get inside, then we can activate that product rule. Okay. What's sine's derivative? Cosine. So cosine parentheses, what goes in here? Just xy, right? We don't do product rule yet, not until we're ready for its own space. Okay, so now we can do product rule, right? Now you can use y prime if you like, but for me, I'm going to use dy dx. I find like dy dx is more descriptive. Sometimes y prime can be looked at as y to the first power, and that can look a little confusing. So I'm going to use dy dx whenever, but it means y prime. If you do y prime, I won't take off any points, but just to let you know that I'm always going to use dy dx. Okay, f prime becomes 1. G is y. Back to f. And in G prime, y's derivative is 1 dy dx. Okay, so all that is to take care of the left side. Right? Oh, I want to make sure we understand something here. This is outside, this is inside. There's a plus inside my inside function. I want to understand, make sure we understand that this is outside, right? That cosine xy is separate from this. It's not this times this plus that, is this times this. Okay, 10x becomes what? 10. So I want to get that dy dx by itself, but it's stuck inside this expression. I'm going to just distribute this through so I can kind of move things a little bit more freely. So I'm going to take this, I'm going to distribute it to both so I can begin to move this around. This is the only term with dy dx. So I'm going to subtract and then I'll divide. Okay, let's go to page 12. Twelve says, or sorry, page 12, number 3. Find the equation of all tangent line for x squared plus y squared equals 4 when x equals 1. So let's go ahead and find the derivative, which will give us our slope formula. Now, how many tangent lines are we going to have when x is 1?
2.
2, right? So at 1, there's a point here. That's going to create its own tangent line. And then at 1, there's also this other point, which will also give us that tangent line. So if I plug 1 into the function, into my equation, I should be able to get 2 order pairs. And then depending on which order pair you're looking at, you can insert the order pair into the derivative to get this slope, insert this order pair into its derivative, get its slope, and then create 2 tangent line equations. Okay, but let's go ahead and build the derivative, right? So derivative, we can tell we need implicit because y is not by itself. There's something done to the y. So go ahead and set up your derivative implicitly. Just want to point out, this is something that I've seen in the past where when students find the derivative, sometimes they see that 4 and they forget that they need to find the derivative of that 4. That 4 is not immune to the derivative process, and they forget to turn that 4 into 0. So make sure you take the derivative of both sides of the equation, not just the left side. So then once we find the derivative, keeping track of our dy dx, there's only one of them, so I just have to solve for dy dx. So this is my slope formula. I'm going to take 1, insert into my equation. I'll get a plus or minus √3. So there's 2 order pairs here, 1 comma √3 and 1 comma negative √3. And then I will take turns plugging the order pair into the derivative to get the respective slope at that point. This is obviously a negative slope, and we should get something that is negative, which we do. This is a positive slope. So when we insert 1 negative √3 into the derivative, we should get a positive slope, and we do. And once we have our order pair and our slope, we can put our 2 equations in point slope form. Okay, last thing that I want to quickly go over here, horizontal and vertical tangent lines. So if I were looking at something like, let's say this equation here, which is obviously not a function. And if I want to find a horizontal tangent line is wherever the graph has a slope 0, then I can find those locations by setting my derivative equal to 0. And when I say setting the derivative equal to 0, I mean the numerator. Okay. So if I want to find out slope 0 and there's a numerator and denominator portion of your derivative where there's variables above and below, you're just going to focus on the numerator. The numerator set equal to 0 will tell you where the slope of the graph is going to be 0. But if I want to find vertical tangent lines, if I want to find out where my slope does not exist, I'm going to be looking at the denominator of my derivative. So if there's a denominator variable, I'm going to set that equal to 0. So if I set this equal to 0, I can find the location where there's a slope 0. So if I want to find slope 0 for this equation, I'll set this, the numerator equal to 0 of the derivative. If I want to find these places where slope is 0 or slope is undefined, I'll set the denominator equal to 0 and find those values. So if the problem ever asks, find the horizontal tangent, you're going to find the derivative and set the numerator of the derivative equal to 0, and that will help you find the location. If you want to find a vertical tangent, you're going to find the derivative, locate the denominator variable, set that equal to 0. Now, what if there was no denominator variable in the derivative? Then basically we don't have a vertical tangent, right? So if there's no variable in the denominator, that means every place on the graph has a slope that's defined. There's no places where slope is undefined. Okay. Okay, so I think that kind of helps us get to through the first part of the notes. I just want to point something out here for your tests. I want to put up a problem here and see if you can help me, or see if you can decide how you would approach this. I did this in the morning review. I recorded it as well. So if you want to go back and watch it, I'll also put this worksheet or some of the problems that I put up here. So if I gave you this problem here, f of x equals 2 root x times x minus 3 squared over 3 square root of x to the 7th. How would you go about finding the derivative?
Distribute and split the terms.
Yeah. So I think the danger is we may look at this and feel, oh, I got to go through chain and quotient rule, but there's no need for that. Okay. And the hints is that there's only how many terms in the denominator? There's only one. So that allows you to split them up nicely. I mean, you can go through product and quotient, or sorry, yeah, you can go through product, quotient, chain, but there's no need to, right? You're doing additional work. And even if you get to the derivative, it's going to be a lot messier than if you just split up. So I just want to kind of show you those steps, what we can do, right? We can FOIL out the entire numerator. We can clean up that denominator. Now, this is careful with this one. Square root of x to the 7 is x to the 7 halves. Okay, it's not 2 7s. It's not 1 7. So this is the most problematic one in terms of students making a mistake and converting this to a rational form. So once you pull everything out, okay, distribute everything through, separate each fraction, bring all the variables to the top, and then it becomes a relatively manageable problem where you can just go through power rule to get to the derivative. There's no need to go through any messy terms. Now, if there's more than one term in the denominator, then you're stuck. Then you have to go through quotient rule. But if there's only one term, split everything up, split them into easier problems before you find the derivative. There's no need to treat it like one large problem. Okay, so I will put this up on the website along with the video, along with the other problems that I did during the review. So you guys can look through it, just make sure that you guys are good. So I'm still scheduling the test for the quiz for tomorrow. But if something changes between now and tomorrow, I will send you a reminder. Okay, or either way, I will send you a reminder. Even if I get confirmation that tomorrow's regular bell schedule, I will send you a text reminder to say, yes, the quiz is tomorrow. All right, come get your phones. The bell's going to ring in like 4 minutes or so. Exactly. Yeah. No homework tonight. Homework will be due on Friday. Yeah.
I need to do my English stuff, right? That's my plan. Stage goals. I tried to move it over. I don't think you guys either. That was the game. No, that was like hard. Like every, and maybe the next 12. Yeah. This is the part where things.
I'm gonna watch the videos.
I think one was like. News reporters trying to use.
Based on the options.
And it was like, yeah, I'm gonna go through mine and check. So. Like that.
Nothing, but try and use it.